Now, often when we deal with this analysis, we use normalized functions in the sense that, like, here's our beam. Okay, in the previous example, we had a beam that basically was running along. This is sort of what we think of as being a fixed guided beam in mechanical engineering. So it had some length L, and we talked about some distance x like this. And you can see that basically x varies from 0 to L. We could define normalized length here, x bar, as x divided by L. And then we've got basically x bar varies from 0 to 1. Okay? And so if you remember from the displacement function that we wrote, u of x was equal to u naught over L cubed. Let's actually flip back to where that was described here. U naught over L cubed, 3Lx squared minus 2x cubed. 3Lx squared minus 2x cubed. And so in terms of x bar, what we could do is we could basically pass this L cubed through into here. And you can see we get u naught times 3x over L squared minus 2x over L cubed. And so we could write u of x bar is equal to u naught times 3x bar squared minus 2x bar cubed. Okay? And now, instead of integrating from 0 to L, we would integrate from 0 to 1. So we're basically analyzing a beam that has unit length. When we do this, we have to be a little bit careful, because if we look at the definition here, we could see that since x bar is equal to x over L, then it's true that L, if we want to calculate, look at dx bar, that's equal to, dx is equal to L times dx bar. Okay? So it also turns out that if we have du dx, okay, that's equal to du dx bar times dx bar dx. And if we look at this expression that I just derived, we got dx bar over dx is equal to 1 over L. Okay? So that means that we end up with a 1 over L du dx bar. So if we're going to use normalized, the normalized coordinates, when we have, in the original unnormalized version, we had du dx, we have 1 over L times du dx bar. And similarly, it will turn out that d squared u dx squared, which was in the bending integral, is going to be 1 over L squared d squared u dx bar squared. Okay? So it turns out that, like, I'll write it down here. So here's the bending strain energy integral, 1/2 EI times the integral from 0 to L of d squared u dx squared squared dx. That's equal to 1/2 EI times integral from 0 to 1 of, I put in here, I put 1 over L squared d squared u dx bar squared, and I have L dx bar here instead of dx. And so when everything is said and done, what I end up with is, in terms of my normalized function, the bending integral is 1/2 EI, sorry, 1/2 EI over L cubed times the integral from 0 to 1 of d squared u dx bar squared squared dx bar. Okay, so this is the normalized bending strain energy integral. Okay, so I should put a little thing on this slide. So using normalized coordinates. Okay, and similarly, if we want to look at how we do the kinetic energy integral, I think this is actually, it's clear why you might want to do it using these normalized coordinates. KE integral using normalized coordinates. So we have the original WK is equal to the integral from 0 to L of rho A U squared dx. Actually, I write it, be careful here. U squared of x dx. Okay, when we insert the normalized coordinates, what we get is WK is equal to rho A times the integral from 0 to 1 of u squared of x bar times L dx bar, right? Because when we change from dx to dx bar, we get this extra factor of L. And so what we end up with is that we have rho L A times the integral from 0 to 1 of u squared of x bar dx bar. And that you could recognize that the total mass of the beam if we had like a rigidly translating beam, well, the total mass of that beam is just rho L times A, okay? So this leading part in front of the integral is the total beam mass, and I realize I forgot a factor of 1/2 here, because we're calculating the kinetic energy. So there's a factor of 1/2. So we could write that WK is equal to 1/2 m beam times the integral from 0 to 1 of u squared of x bar dx. Okay, another useful thing. So we're calculating a kinetic energy integral in normalized coordinates here. We end up with it. The way we calculate the kinetic energy integral is basically the integral of the displacement squared. Okay, so the integral of the displacement squared. Okay, now I'm going to talk about using the Rayleigh-Ritz method for calculating the natural frequency of a double-ended tuning fork. This is called the double-ended tuning fork, this structure, because normally if we think about a sort of a conventional tuning fork, right, it looks like this. And the tuning fork vibrates, right, these tines sort of vibrate back and forth, and then this part here is the part that we hold in our hand or is fixed. So this is called a double-ended tuning fork, because you can see there's basically two ends here, right? These things are, basically these are anchored here. And then this part is the part that's vibrating back and forth, right? So they sort of undergo vibration this way and this way. Okay, I'm going to get rid of the second one. So this is the vibratory motion of this double-ended tuning fork structure. Here's a double-ended tuning fork structure that has driven by a comb drive. So again, this is the double-ended tuning fork structure. It's excited by the comb drive motion here. Okay, these are called double-ended tuning forks. So this is a single-ended tuning fork, and clearly this is a single-ended tuning fork stuck basically symmetrically about the middle. Now we can treat each of these tines of the tuning fork as being a clamp-clamp beam. And so if we look at a clamp-clamp beam, these are the mode shapes here. The first, second, and third modes look like this. And it turns out they're described by this function. This is phi, and what we're using here is the what is shown as epsilon here is what I called x bar. So it's the normalized x-axis coordinate. So epsilon is x divided by the length of the beam. And in this mode that we're calling these phis are the mode shapes. Phi1, Phi2, and Phi3 are the mode shapes for the first, second, and third mode. We can see that the first mode has its maximum amplitude at the midpoint here. This is at epsilon is equal to 1/2. And this one, they didn't even try to figure out where it is that the maximum is. It's somewhere. I don't think it. I'm not sure actually if it's at a quarter of the length or not. But the other thing to point out is that if you notice, these have amplitude 1. Okay, and so this expression here is for the normalized mode shape You see it's got sinh in there and cosh, hyperbolic sine and cosine, and also regular sine and cosine. And here are these parameters alpha, beta, and kappa that are used in this function. So kappa is the overall amplitude, and beta and alpha are these other components here. So beta we can kind of think about as being like the wavelength of the vibration. And kappa here is chosen such that the normalized amplitude is equal to 1. If you remember, like when we're doing Rayleigh-Ritz, if we just want to calculate frequency, it turns out that it doesn't matter what kappa is because the amplitude doesn't matter. Okay. Anyway, this is a table that tells us what the normalized mode shapes are for a clamp beam for the first, second, and third mode. So we could write basically this one is phi1, phi2, phi3. Okay, and this is on your homework, so you probably care about what this is. All right, so how do we use this? So I'm going to analyze two cases, one with no residual stress, okay, and the second case where we have some residual stress of 30 megapascals in the film, and we're going to model the comb drive as a point mass with m equal to 1 picogram. Okay, so it's that point mass is in the middle of the structure, and it has mass of 1 picogram. And the dimensions here, the length of the tines of the beam, which is this direction here, this is L, this is the big L, 200 microns. The thickness of the film and the width of the beams are both 2 microns. It's made out of polysilicon, so 150 gigapascals Young's modulus, and the mass density is 2.3 grams per cc. So these are the parameters for polysilicon. Okay, and what we're going to do is it says use the first mode shape for both cases, and we're going to analyze a single tine. So we're going to assume basically phi1 of I'm going to call it x bar is our normalized mode shape, and we have to calculate the WK and WE, the kinetic and the elastic strain energy. So let's do this. Okay, strain energy, WE, is going to be equal to W bend plus W due to the residual stress, sigma. Okay, and in the case where sigma is equal to 0, this term is not going to be there. Okay, right. So that in case 1, there's no residual stress. And these integrals came from lecture. Actually, these integrals, in fact, came from lecture 10. And I think some of them are from lecture 11. Okay, so the bending energy integral WB is equal to 1/2 EI over L cubed. Remember, I just derived how you write this for normalized functions. This is integral from 0 to 1. D squared phi 1 of x bar dx bar squared dx bar. Okay. And the residual stress integral W sigma is equal to 1/2 sigma, what did I call it? Sigma R. I guess I called it sigma R. 1/2 sigma R times B times H times 1 over L, because we're dealing with normalized functions, integral from 0 to 1 of D phi1 dx bar squared dx bar. Okay, so this is the residual stress. I'll write it over here. This is due to bending. Okay, and the kinetic energy integral WK WK is equal to the integral 1/2 rho B H L times the integral from 0 to 1 of phi1 squared of x bar dx bar. Okay.